Hello, everyone. My name is Sasha Lazarevic, and this is a meetup of Quantum Serbia. Welcome to our 23rd event since this community was created back in 2020. And today we have really honor to have with us Isa Tippens, who is going to talk about quantum tokens. So we're going to learn something new, and especially for me, Isa, thanks a lot. This is really lucky coincidence because recently I got a question about quantum tokens. I didn't have any clue what this is. So really, when I learned from Alexander, that there is opportunity that you can talk about this, I was just thinking, well, wow, I'm going to learn about this. So yes, let me just read a little bit the description, the abstract of this topic today, so that everybody is on the same page, and especially for those who are going to follow this event now or who are going to watch this video later on YouTube, so that you know what quantum money or quantum tokens is about. So we are going to talk about a framework for secure financial transactions with relativistic quantum tokens. So research into quantum money dates back to the 1980s with security rooted in the no cloning theorem and the inherent uncertainty of quantum measurements. However, practical implementations have been delayed by the absence of quantum memory. So in this project now that Isa is going to talk about bridges the gap by integrating quantum and classical techniques to demonstrate a proof of concept transaction system. So this project combines quantum key distribution, hashing, GPS-based time synchronization protocols to create secure quantum banknote framework. So, and this framework will enable anonymous generation, exchange, verification of quantum banknotes while maintaining robust security against counterfeiting. So, really exciting, novel. Looking forward to hearing from you, Isa, today. So, for everybody here, please mute yourself and so that we avoid the distractions. And please use the chat of this Zoom meeting to ask your questions. At the end, we'll have a question and answer session with Isa. And also, I let Alexander Radovanovic, professor, who helped to introduce Isa to our community, to say a couple of words about Isa.
Yes, so Isa is a computer science student at the University of the Western Cape in Cape Town, South Africa. He's studying towards his MSc degree in, of course, computer science, and his focus is on quantum computing, quantum cybersecurity, and especially in quantum money. Isa, in addition, is also works as a software developer in fintech, and he's a mentor for the cybersecurity group at the University of the Western Cape. Okay, Isa, now you can start, I guess.
Page is yours. Please share your slide deck now. I think you can do it.
Is everything worked? Okay. Thank you, Sasha. Thank you, Dr. Aronovich, for the introduction. My name is Isa Tippens. I am a MSc Computer Science student at the University of Western Cape. I'll be presenting my thesis on framework for secure financial transactions with relativistic quantum tokens. The thesis is supervised by Dr. Norman, senior software engineering lecturer at the University of Western Cape, and co-supervised by Dr. Radovanovic, research fellow at UWC with a focus on quantum computing. And Dr. Radovanovic is instrumental in this project. He's introduced me to this concept. He's keeping me engaged with all the fun new topics he finds, just keeping the magic alive. This thesis is also funded by South African Quantum Institute. They are South African-based group, quantum group that connects 5 universities, encourages and funds topics and research developments in quantum computing. Slide. So with this project, I've developed a digital currency that utilizes cryptography for secure transactions in the near future quantum world. What we try to address here is the fast-growing direction towards digital assets, digital payments. So, for example, your credit card paying by PayTel or clicking a link to perform an online transaction. These are all secured using classical communication and classical cryptography, such as encryption. But we have the ever-living threat of quantum supremacy. The idea that algorithms such as Shor's algorithm and Grover's algorithms will one day become feasible enough with quantum technology that we can break these encryption and then utilizing and making these systems insecure. So there's two approaches to this problem, being quantum resistant algorithms. But with this project, we went with the quantum alternative, simply taking a classical system, transactions, seeing what we can do to improve it using quantum techniques and algorithms. We also built this project using Qiskit, a library, Python library designed by IBM. This is also tested locally and simulated locally and tested online using IBM's quantum cloud platform. The main research questions behind that this project attempts to answer is what is the possibility and feasibility of a quantum transaction system with the current quantum hardware that we have today? We want to see where we are with implementing quantum solutions using existing hardware and what's remaining, what's missing, where can we go from this? The second being, how can we ensure a transaction system that's secure using quantum techniques from end to end? It's not as simple as replacing the insecure sections. We need to make sure everything at every communication stage, every secure storage part of the system is secure. Uh, Before I go into the actual details of the project, just go a bit of a background. So back in 1983, Stephen Wiesner published a paper titled Contracoding. This is a encoding protocol that allows you to transfer two messages, but only one can be read. The magic here is that the qubit is for each qubit in the stream is encoded using the message binary bits of two messages. The receiver only selects one basis to measure in, and by doing that, they destroy the second message and only receiving one message. Not effective as a communication protocol, but it spawns many fields from this point onwards. First being quantum multiplexing, the combining multiple messages into one. Quantum cryptography, we later see Gilles Brassard and Charles Bennett develop BB84 and B92, the earliest quantum key distribution protocols. I'll later go over BB84 as it's an important aspect of this project. And then finally, the big portion of this paper that's not yet fully realized is quantum money. Wiesner theorized a hypothetical banknote that stores qubits using his protocol, simply qubits in the standard basis or diagonal basis. The idea is that these qubits are protected using, sorry, these qubits are fragile. The the banknote is qubits are, I'm sorry, I'm lost. Uh, the fundamental portion of this banknote is that it relies on the no cloning theorem. Qubits, if you don't know the initial state of a qubit and how it's prepared, you cannot copy it. As well as probability of guessing these qubits correctly as being a counterfeiter. There's a 3 1/3 chance of correctly guessing a qubit, let alone if there's 20 qubits, you only have a 0.317% chance of guessing it correctly. You can see why this might be a better alternative. Simply just having a banknote, trying to copy it, destroys the banknote if you get it wrong. But the only issue is that this wasn't implemented in reality as quantum memory is limited. Qubits can only remain coherent for long enough for a few nanoseconds. Another more recent paper by Adrian Kent, a professor at the University of Cambridge, was a classical transaction protocol that emulates quantum money through bit commitment. The money is distributed and travels through trusted nodes until it arrives at an expected redemption point. How does this work? It uses the BB84 protocol, where instead of completing the protocol, the Alice sends the money bits to the BB84 bits to Bob. Bob sends it to Charlie through trusted network, but only the basis states. The bank Alice sends her the verification part of her BB84 protocol to another trusted node, and each trusted node they verify a certain subset of the basis states. At the final point, when Charlie receives the incomplete set of BB84 bits, Alice will have a trusted node there where they compare the BB84 states, and at that point, if it passes verification, the transaction completes. The idea behind S money is that money doesn't exist until it's perfectly verified. Therefore, it is summoned once the transaction or the BB84 bits are verified. In a more recent paper in 2022, this was practically implemented in an experiment where they used a more photon detector and a laser, where they emulated the S-money protocol with success. In a 2024 paper, they were able to implement this using fiber optic cables between two cities in China. Yeah. Well, before we even go into the project, just a little bit background into qubits and quantum mechanics. Qubits are a two-level system that represents a basic unit of quantum information, senior of the block sphere. They can exist in a superposition of values of either 0 or 1, or more generally, a linear combination of 0 and 1, or more generally, a linear combination of multiple states. Say, for example, two qubits, superposition of that would be 0, 0, 0, 1, 1, 1, or 1, 0. A data superposition exists in all of those states at once until they collapse to one of those states. The probability of measuring one of these states is dependent on the amplitude of the state. And qubits will collapse once they're measured, losing all the quantum information, and you have your classical results. At a physical level, qubits are either atomic particles such as photons, electrons, or ions, and they're represented using direct notation or brackets. So just as a quick example of encoding data, this is quite similar to how BB84 works. You would decompose your classical text into binary bits. For each binary bit, you would uh, select a basis state, either standard or Adamant basis. For zero bit, you would simply leave the qubit alone. For 1 bit, you would apply an X gate. If you select an Adamant basis, you would apply the Adamant gate, which puts the qubit in superposition. Therefore, you would have a qubit that's in superposition. If you measure it like that, you would either receive a 0 or 1.
Isa, sorry to interrupt.
Yes?
May I ask if you can just talk a little bit slower, because sometimes we have a bit of audio interruptions, very small interruptions. So if you slow down a little bit, then it's going to be clear.
Okay, I'll try. Thank you. Sorry about that.
No, it's not a problem.
Oh.
Thank you.
So a notable feature with quantum computing is that quantum gates are reversible. Quantum operations are reversible. If you apply an ANOMA gate and apply it again, you receive a normal qubit. If you apply an X gate and apply it again, you receive a qubit back in the 0 state. So example, yeah, when Bob receives his stream of qubits, he guesses which state to measure in. If he measures a standard qubit in a standard state, he receives either 0 or 1 as normal. Whereas if it was an automat, it was a qubit in superposition or 1 with a 50% chance of occurrence. Another fundamental concept in quantum mechanics is entanglement. This is where multiple quantum states are highly correlated with each other regardless of the distance of separation. Say, for example, I have two qubits that are entangled and they're both set to the basic set of 0. Measuring both qubits will always receive 0. If one qubit is in superposition, they're both in superposition. Therefore, they're both either measured 0, 0 or 1, 1. As a test here, we tried entangled qubit on IBM Kiev, running 1,000 shots. As you can see here, the bar graphs, both measurements have like a 50% chance of, both qubits have a 50% chance of being the same. Whereas the noise on real quantum hardware, there might be a few discrepancies there. In quantum computing today, there's various amounts of processors with varying amounts of qubits, some in the hundreds, even now in the thousands. IBM, Microsoft, and Google allow access via the cloud in large cloud data centers, but they're mainly used for research purposes as they cost quite a lot per circuit that you run, even per shot or amount of qubits. There are many software frameworks for programming circuits and simulating them using Qiskit, CirQ, or Qsharp. A notable GPU is the Microsoft Majorana 1. It's a topological GPU known to today that Microsoft has developed using Majorana particles, with the promise or advantage of being a noiseless GPU. Qubits can also be transmitted using photons. Quantum key distribution allow for better security over classical cryptography. There's classical encryption algorithms such as RSA SHA-256, which is expected to be defeated by quantum algorithms such as Shor's and Grover's algorithm. QKD protocols mainly rely on the no-cloning theorem or also entanglements such as E91. If eavesdroppers were to intercept your key during transmission, to make it useless, and the interference of these qubits will be detectable towards the end of the stage of these QKD protocols. There are also QKD devices that are commercially available which can utilize existing fiber optic systems. These are used also in some banking institutions for more secure communication between banks. Now onto the main project. So we made a quantum banknote, which is a digital asset or more of a digital token that we transact using the system. We try to make it unforgeable, try to make it tamper-proof and verifiable, easily verifiable and unique. Each banknote has a serial number, which is a classical string, a quantum state, which is shared using BB84, a validity timestamp, which is a usable programmable timestamp, which determine when a token can expire if it's redeemed later than that, and a usable programmable location for token redemption, where the token can be used, and if it leaves that area, it cannot be used. So this is the main process of the protocol. It's a simple cyclical system. First, Alice requests an issue, the bank issues. Alice will send token to Charlie. Charlie will verify with the bank, and the bank will then confirm with Charlie if the token is legitimate. To keep it simple and just to reduce any complexity where it doesn't need to be. The architecture diagram here, just a more expanded version of the process I showed now. Just to note that the red lines indicate a quantum communication where we use superdense coding to transmit classical data, purple for the BB84 transmission, and green for classical communication which is less sensitive data. Alice requesting doesn't need to be communicated securely. There's just a more UML diagram of the architecture. This will just be more verbose explanation of how the first one being the sharing of its quantum state being BB84, second being the final transaction with Charlie. Okay, so just to explain the individual parts being issuing, verification, and transaction. When Alice requests a token from the bank confirms if there's a token available for Alice. It then begins generating a serial number, a classical string, and a quantum state using BB84. I'll explain in more detail how superdense coding in BB84 works, but for now, the banknote itself will just exist as a serial number and a quantum state when Alice receives it. The bank records the collapsed BB84 state in the database assigned to the serial number, sort of a key value map, as you can see. Alice also stores the BB84 state as a collapsed classical state. And just a quick simple example of BB84. Bob the bank will select a random bit or basis, bit being the actual bit value and basis being center other mod. if Bob selects a 1, he will apply the X gate. If Bob's second bit is a 1, he then applies the automatic gate. When Iris receives the qubit, she doesn't know if it's in the standard or odd mode basis. Therefore, she also has to guess 0, 1 standard odd mode. After Alice applies her gate on the received qubit, she measures it, and then Alice communicates the bases that she measured with to the bank. After all the qubits have been measured, Alice and the bank confirms with Alice which basis states were correctly used, and Alice discards the incorrect ones. This way they can synchronize a key without directly sending a key as plain text. Simultaneous coding is a quantum communication protocol. It utilizes entangled qubits to securely send data to another party. For example, here Alice sends her H letter to Bob using 2 qubits at a time. Alice entangles the qubits, sends the second qubit to Bob, and then on the first qubit, Alice applies an X gate if the first bit is 1, or a Z gate if the first bit is 1. Since the qubits are entangled, the quantum information will be modified on both the qubits. On the second qubit, if the second bit is a 1 where the Z gate is applied, Bob's received qubit will be set to 1. After Alice applies all the gates, she will send the last qubit to Bob, and then Bob will then measure the 2 qubits without any other modification. During transacting, Alice will then have to send the quantum banknote to Charlie. Alice does not want to send the exact state to Charlie, otherwise Charlie is able to duplicate the token. By doing this, how we solve this is by using a quantum hashing function. Alice requests from Charlie his preferred time and location and his current location. The time being the time the transaction should happen before it expires, and the location of which Charlie is. Alice then takes the information, hashes it, and sends Charlie a classical token, the serial number and the token hash. How this hashing works is we just take the data, remember the quantum state is a collapsed classical state. We apply a geohash function on the validity period, just simplifying the data. And then after hashing, we receive the classical token. How we went about classical quantum hashing is there's 2 approaches we are currently testing. First being a simple deterministic hash function. We take a binary string, say 1 byte, split into 2 4-bit pairs, and then depending on the value of the bit, we apply a rotation on the x-axis. If it's a 1, we apply rotated pi degrees on the qubit, and then we apply a second stage, first phase and a second phase where we run a few CNOT gates. The smaller dot is a control, and a plus sign indicates a not target. The not just applies a not operation on the qubit flipping the bit. And just an example of how this would work with this algorithm. The header will become a hash. The second hashing function that we did is a Grover-based. Grover's algorithm is a quantum algorithm for unstructured database search. It offers a O of n O square root of n. Worst case, if searching for a specific element in an unstructured database, whereas a classical approach, we have to search every single element for the target element or solution. This affects symmetric cryptography and hashing through preimage attacking, find the original input of the hash. But in this case, we flip the script and just try to use Grover's algorithm to generate the hash instead. Say, for example, our text here, we split it into 4-bit chunks and apply Grover's algorithm. Grover's algorithm requires an oracle function or black box function that identifies the correct solution and then flips and applies the X gate on the quantum state, on a specific state. And then goes through a amplification or diffusion phase where they tries to increase the amplitude of the target state. Repeat this constantly for the first chunk until until it evolves into a set determined solution. But the next chunk, which then modifies the hash slightly into another solution. And at the end, we receive a hash. In the verification phase, the bank would then need to recreate a hash to verify with Charlie's token. By doing this, confirms that Charlie has received the correct state from Alice, as only Alice and the bank knows the original quantum state that was sent between the two. By doing this, Charlie will need to send the serial number, location, and validity period. The bank will then fetch the serial number from this database and then recreate the hash. And then verification is simply just a classical step of checking the time. Does the timestamp of the bank match before the validity period? Do the two hashes matches? What can be realized here is that there's no way for any party to be dishonest in any part of the transaction. If Alice modifies her quantum state at any point, it would yield a different hash that the bank doesn't match. If Charlie lies about the location or the validity period, the hash will match. Therefore, it can be both parties will need to just be honest in transmitting the correct information. Another idea that spun off of the validity period is the time synchronization. If Alice would like to transact at a certain time, the bank would also have to have the exact same time as Alice, or vice versa. What we've done here is a time synchronization protocol where Alice and the bank can synchronize clocks so that they can perform the transaction efficiently and not no discrepancy where Alice sends a transaction where her time matches, but the bank's time after the period. We do it by sending two entangled qubits and measuring them at certain schedules. The idea is that qubits lose coherence over time. The quantum information slowly lose coherence, they disappear. And then if they were to measure at the exact same time, the qubits will be at most coherent, and then the results will be mainly the same. Decoherence, the confirmation starts to loses information. The results become noisy and they won't match. So just a simple example, three different intervals, 12 o'clock, 5 past 12, 10 past 12. Alice's clock is slightly ahead or behind the bank. The first set of qubits come out and they measure, compare results. Only one set of qubits are matching. After that, Alice adjusts the clocks forward or backwards. At 5 past 12, Alice's clock is, let's say, even further away from the bank's. Therefore, when they receive the qubits and measure, the resulting measurements are completely incorrect. Alice adjusts the clock again, and then at 10 past 12, the clocks are matching. They see the qubits, they both start measuring at that time, and then the measurements are completely correct. There's no coherence loss. They both received the correct time, they both received qubits at the exact time at the same time. Cool. Currently testing a working prototype that's almost in the final stages. That simulates the entire process. I can see here there's the three quantum stages being just abstracted away. Generate the quantum state at number one, hashing the token number two, and then the bank hashing token number three. It doesn't yet implement superdense coding or time synchronization yet. Those were separate tests. Just getting simulating quantum network was a bit difficult at the time, but we're almost getting that right. This is just a example of the working program. BB8 for states being received, bank issuing a token, electronics information, creating the hash, checking if the hash is valid, and such. And this is just a testing all the time synchronization. We simulated the decoherence by applying a dephasing model on the identity gate. An identity gate simply doesn't do anything to a qubit. It just doesn't make any modification to the qubit. But applying a noise gate, once the qubit runs through this gate, it'll lose coherence or simulate the decoherence by dephasing the qubits. And by this, when we simulate the schedules, we take the schedule's time as this clock, take the time difference, and apply noise based on the time difference. If the clock matches the schedule, then we apply no noise. Therefore, the results should match. As you can see here at the bottom graph, the first schedule from the bottom, as this clock is slightly off, it's not very, the correlation between the qubits aren't above 60%. Change the schedule, change the clock, and the schedule comes lower. At the third schedule, her clocks match, and then gets a 100% coherence. The graph on top, just simply the amount of correlation between the entangled qubits and the decoherence over time. Up to about 9 seconds is 20% coherence or correlation. This is just a test with the simple hashing function. This is
Isa, is that only me? But I see that it is frozen. Actually, Isa, can you hear? Okay, Isa, now I think the video is back. We had a small interruption where your image was frozen. Can you please talk again so that we check?
Can you hear me?
Yes.
I think I was just
Oh, yeah, go just back to your slide deck.
okay. Let me get back. Do you know how far back it was?
Yep. Okay. So you were at the beginning of this slide.
Hashing slide.
Thank you.
Okay, perfect. I'll just present. This is all good? Okay, perfect. Sorry about that. I'll just start from the beginning. So this is a heat map of a Hamming distance graph. Hamming distance refers to the number of changes in a hash when you change the bits in an input string. The idea with the hashing function is that if you make a slight modification to an input string, the hash should be vastly different. The idea, as you can see here, darker colors means very little change, brighter colors means greater change. From top to bottom is 1 bit flip to 10 bit flips in the input, and then from left to right is the size of the input. Or the size of the hash length, sorry. A uniformity test of the deterministic hash function. There shouldn't be a bias towards the characters used in a hash function or generated. A perfect hash function would have a uniform distribution, so all bars are lining up. While this has most of the bars lined up, there's a zero character that just doesn't get or used in the generation process. Why, we're not sure yet, but I need to work on figure it out. And this is just an evolution of the measurement probabilities. Since it's a deterministic algorithm, the individual hashes that can occur will be 100% at each stage of the hashing generation. If we had used superposition or entanglement, you'd see a broader range of colors at each stage. But with the Grover function, we will see this. Yes, the Grover-based function at the initial stage, the entire state is in superposition. At the first chunk, it'll lapse to one state and slowly merge into different states until we get the final state here, 1001, which is the most likely hash that it found or generated. Okay. So a future approach to this project would be a decentralized approach. We went with the centralized approach since it's I would say, more simpler approach. with a decentralized, you need to somehow share the encryption keys or public keys, but we don't have the limited available quantum memory to store one keys so that any person can verify at any point, allowing publicly verify public verification. Yeah, so there's also the other issue of instant verification, also privacy. While we allow for some sort of privacy with centralized, there's not very instant verification. There's not complete privacy. Decentralized would allow for some form of privacy and some form of instant verification without the need of going to a bank to allow for going to a bank to prove that the money is valid. Decentralized allows people to simply go up to a merchant, give the token, and token can be verified at that moment in any time. So in the end, the current stage of the banknote is a proof of concept. We managed to utilize BB84 as a secret state that's not necessarily for encrypting, but more for a secure identification of a proof that this banknote came from someone. Surveillance coding for sending the banknote data securely. Quantum hash function for converting the banknote into a shareable token versus a classical hash function. And then time synchronization that utilizes decoherence of entangled qubits. There are multiple other time synchronization methods, but there's nothing that we come across that uses this method of decoherence and schedules. What's remaining for this project is just to do a security analysis and performance analysis. And then some consideration limitations we've discovered is that it's very susceptible to noise. Idea is that uh, if the noise were to affect the state, the hash would be completely off. The bank and the hash would match. Alice's hash would match with the bank. So for this project, we just ignored it. The idea is that quantum computing is heading towards a noiseless form, as we've seen with Microsoft's Majorana one. And right now, the software exists as an emulation of the communication between the bank and Alice. Ideally, we would want to utilize this on the actual hardware at some point when you get there. Okay, thank you.
Great job, Isa. Thank
Thank
you
you.
for sharing the insights from this wonderful work here. So yeah, let's see what are the questions.
So can I start with the questions? So like a big picture question. So what is the difference between quantum token or quantum money and the current system we have? They're talking about digital currency, and of course we have money like Bitcoin. So we have like two types of digital money. So what is the main difference between your project and the existing
Okay.
type of digital money, like
Um,
cryptocurrency and digital money?
so I'd say there's a lot of similarities. This is a digital asset or digital currency in its own form. It differs from cryptocurrencies not being decentralized at the moment, but it's still centralized. Uh, it's also a quantum token. The idea is that even though we having the approach of quantum money, it can be applied as let's say, an arcade. Go to arcade, you have your own quantum tokens. Um, it's a very general use case for this project. Um, yeah, and the part of it being a relativistic quantum token, the money doesn't necessarily exist until the point of transaction. Whereas physical money, you have it in your hand, it's always money until you give it to someone, so it's still money. Our token exists in the point of moment where it's needed. Um, yeah, I hope that answers your question.
Yes, thank you.
So basically the digital currency, it exists as a token. And here we are talking about a token that is being created only for a particular transaction, right?
Right. So the S Money paper that we referenced from is inspired from that, where I forgot to mention where it's they want to use it as like an interplanetary way of transacting. The idea is that you can send your money out and don't have to monitor constantly. It only comes back to you if it's confirmed or not. The money state is sent to another city or another planet, gets verified there, and then you'll know if it's successful or not. But the idea is that it propagates using lights or lasers. That's the fastest way you communicate.
So if I'm not mistaken, it's almost like a Schrodinger cat. Is it dead or alive, or is it exist or doesn't exist? And it
Yes,
exists only if you see it. If you don't
yes,
see
yes.
it, there is none.
Any other questions? Feel free to type here if you don't want to mute yourself. But Isa, if I understand well, so the quantum computer or quantum way of calculating or transmitting the information is used here twice, actually, if I understand well. Once is to calculate the hash function, right?
All
And the
right.
second time is to send the information from Alice to Charlie. Is that so? This is a using the quantum key distribution, or maybe I just mistaken. One.
Um, got yeah, you got two of it right, or most of it right. There's mainly two sections. I would say quantum communication and the quantum cryptography portion. Cryptography being the hashing and the BB84, communication being transmitting BB84 state and superdense coding. Superdense coding just simply a way to send data over quantum line, quantum tunnel. And then the quantum cryptography, the hashing. This is a circuit that hashes data into a hash, and then as a replacement to classical hashing where it relies on mathematical functions, this simply uses gate entanglement or superposition rotations on qubits.
Okay. Yeah. Okay. I see.
So what I also find interesting that in the hashing algorithm use quantum interference, which is maybe something new. So we don't have any mathematical functions. We are using quantum effects like superposition and quantum interference.
Yes, it's in the Grover-based hash. Um, Amplification portion, there will be multiple states that are picked by the oracle function, and then amplification just uses interference to propagate or increase the likelihood of one solution.
Yeah, so in a way we combine like, is it a wave or is it a matter?
Yes.
So this is basically the intersection between quantum computing, quantum algorithms, and then cryptography and finance. Am I right, or did I miss something there?
It's a hybrid of everything. So hybrid computing, classical quantum computing, hybrid in finance with computing computing. Yes.
And how feasible it is. Of course, it's a feasible in your test bed, so I guess everything works. But if you want to put it on a cell phone, so how feasible would that be?
I mean, at the current moment, as mentioned now, the quantum hardware, there's a lot of noise. The system at the moment is also susceptible to noise. Um, but the idea behind is that we working towards a future where quantum hardware is noiseless. That way, this project would be able to work on there. At the moment, there are some portions that would work well, but not fully at the moment.
And Isa, in the beginning of your presentation, you referred to a couple of research papers. What is actually different in your work comparing to those previous research?
Let's say with Adrian Kent's S money. Well, we try to leverage the summoning or super money portion where money exists in a transaction point. The difference here, we try to adapt a classical system of a transaction. Let's say with classical, we have digital signatures proving that something came from some authentic person. We replace the hashing portion with a quantum hash. Essentially, the hash itself becomes the money. Um, Whereas Reason's paper is simply just a banknote with qubits on a physical banknote with qubits in a device. It wasn't feasible at the time, isn't still feasible now. S money is somewhat feasible, but still it's different in that it's not a like a public system. The bank just simply sends out BBA4 states to someone. Someone sends out BBA4 states to a few nodes until it eventually arrives at the destination.
Okay. And to create the token, actually, so you're using the geolocation and the timestamp, which means that actually you can include in this hashing function different, like even more complex parameters or conditions, right? So this can be a kind of linked to some kind of contracts or transactions, or is
Yes,
that the big idea that can be developed out of this solution, or think about that?
sorry. The other thing we want to solve was privacy. We don't want the bank to know where you're going with your funds or where exactly you're going to spend it. They're still fine about the end when they verify the token, but the idea is that you can take your token and use it another time. Um, as well as the Charlie will give the exact time and location where he is, and that allows the bank to know that this is coming from Charlie and also from Alice, not someone who has Alice's token and such.
Okay. I'm talking a lot, but really I'm inviting everybody, all participants. If you have any questions, feel free. And so, for example, ISA for large-scale implementation, what are the resources that one would need? I mean, how many, what kind of qubits or what kind of transmission protocol or how many qubits or things like that. So how many quantum processors you would need? Every party here should have a quantum computer, or this would be centralized, or what are the resources needed for that?
For the current stage, we work with a very minimal amount of qubits, essentially for hashing, I'd say 8 or 16. And then also a QKD device to send, or communication line to send data between two parties. But yes, everyone would need a quantum computer or a hypothetical computer or quantum communication device.
The personal question is, what got you into in this project? How did you get excited about this?
Um, in my honors year, 2023, I was still working in fintech, like a very small early stage, and then I came across a list of topics, and quantum computing was one of the topics, and quantum money, and I just it like aligned what I was working at work and was interested at the time. So just I never had any experience with quantum computing. I heard about it on the news, I saw it on YouTube, so I just decided to just go for it, and I learned a lot. I like understand it better now, like all the mystery behind it. Like I enjoyed it even more knowing what's going on behind.
Okay, so this is part of your master
It's about
program.
my master's.
Yeah.
Yeah.
So when do you
So,
expect to close it and to do your thesis
uh,
presentation?
planning to finish end of this year, hopefully. I think Dr. Raj can give a better outline than me, but it's we in the I'll say final stages of getting everything together.
Okay. And for the future, do you plan to stay in the research and learning further, or maybe to try to commercialize this through a real world project, or what are your plans?
I'm still very much interested in the quantum computing space. I don't intend on continuing studies after this. Maybe eventually down the line, but yeah, the issue with this is I'm not too confident that at the current stage we can still see it's not very feasible to implement with current hardware. You can see how far we've gotten. It is feasible to some extent, but we don't have mobile devices to make this work. We don't have public or home-based um, quantum computers or quantum devices to make this happen.
Yeah. Okay, thanks a lot, Cesar, for sharing all this. So if there are no questions, I'm going to stop the recording and then we will close this session.